Hello class, welcome to this lesson on 4.5. We're going to be talking about the general multiplication rule and tree diagrams. Alright, so the essential question is how can I use a tree diagram to model a chance process involving a sequence of outcomes in order to find conditional probabilities? We also want to address the question how can I find probabilities involving two or more events joined by and? So probability of events A and B, for instance. So learning goals are to use the general multiplication rule to calculate probabilities, use a tree diagram to model a process involving a sequence of outcomes, and to calculate conditional probabilities using tree diagrams. So the vocab includes the general multiplication rule and tree diagram. So let's talk about the general multiplication rule. Remember that in last lesson we were able to find the probability that event A or event B happens by using what we call the general addition rule. So the probability of finding A or B, which is the same as the probability of A union B, remember recalling that this is the union symbol, and we simply just added the probability. So we added the probability of event A plus the probability of event B, and then we got to take away what they have in common. Remember that this is the intersect symbol, and that stands for and. So we take away what is common to both A and B. Now remember that um, if A intersect B is equal to 0, then this simply means that events A and B are mutually exclusive. And if they're mutually exclusive, that means they have no overlap and they cannot happen at the same time. And therefore, the addition rule simply becomes A plus, or P of A plus P of B. Now, for the general multiplication rule, if you want to find the probability of that event A and B happen at the same time rather than or, we use the general multiplication rule for this purpose. So the general multiplication rule states that for any chance process, the probability that events A and B both occur can be found using the rule. And remember that the other symbol for and is the intersect symbol. So we have P of A intersect B is equal to P of A times the probability of B given A. Remember that this is the conditional probability right here. And that is the multiplication rule. So you basically multiply the probability of both events occurring. So remember that this formula actually comes from the formula we talked about in the previous lesson. So in the previous lesson, we had the formula for the conditional probability. And recall that the formula was this formula right here, and it was the probability of B given A was the probability of A and B divided by the probability of A. So if you multiply both sides by P of A here, if we multiply both sides by P of A, then the P of A's cancel, and that leaves us with the formula that we have here. P of A intersect B equals P of A times P of B given A. So really these formulas are really linked to each other, and so they're intertwined. So multiplying both sides by P gives us the formula above, and what this formula here is saying that for both of the two events to occur, first one of the events must occur, which kind of makes sense. If both events have to occur, that means one has to occur first and then the other one. So when one occurs, let's say A, well then we need to find the probability that B happens given that A has happened already. And that's what this formula is saying. And if you want to figure out those probabilities, you just got to multiply those probabilities and given that the other one occurred. All right, so let's talk about the rule, the general multiplication rule, specifically for independent events. So if two events are independent, it does not matter which one occurs before the other. So the probability will remain the same regardless of whether, for example, event A happens before event B. So if we're talking about this probability here, the probability that B happens given A, well, in this case, it's going to be the same as the probability of B happening. It doesn't matter if A happens or not, it's not gonna affect the probability for B. So an easy example is, let's say you're looking at the weather and you want to go sporting outside. Let's say you want to go playing basketball or something outside, right? Or football. Well, in that case, the probability that you play that it rains, given that you go sporting or you go outside, will not change. The fact that you go outside will not change the fact that it rains, right? So in that case, the probability, for example, in this case of raining, given that, let's say, I don't know, you play football or something, well, the fact that you play football is not going to impact the fact that it rains, and therefore the probability here is simply still going to be r, right? It's still going to rain, and that chance is still going to be the same. So in that case, that kind of is telling you that they're independent of each other in this case, just by looking at that. Now, if we're talking about two independent events A and B, the general multiplication rule turns into this. Now we know that A does not impact B, therefore we know that this transforms into probability of B, and therefore we get a simpler looking formula. So this formula is only useful for independent events. All right, so let's look at a problem that involves the multiplication rule. So the Pew Internet and the American Life Project found that 93% of teenagers use the internet and that 55% of online teens have posted a profile on a social networking site. Find the probability that a randomly selected teen uses the internet and has posted a profile, and show your work. So we want to look for the probability that a teen uses the internet. So we'll say internet and has posted a profile. So we'll say probability of internet and profile. Okay, so if we look at the multiplication rule, well, this states that I can do the probability of internet times the probability of someone posting a profile, given that someone uses the internet. Okay, and that's using the formula of the general multiplication rule, which states that P of A and B is P of A times P of B given A. Okay, so then what's the probability that someone uses the internet? Well, it says 93% of teens use the internet, so this is going to be 0.93. Now, the probability of that someone posts a profile, given that they use the internet, well, it says that out of the 93% of teenagers that use the internet, 55% of those have posted a profile. So this 55% is a conditional probability. So this 55% is actually the conditional probability for this guy. So it's going to be 0.55. So it's pretty straightforward. They already gave us both those numbers, so we just simply multiply them, and that leaves us with 0.5115. All right, so now let's talk about tree diagrams and how they relate to conditional probabilities. So let's look at an example. Let's say that Steve hits the snooze button on his alarm on 60% of school days. If he hits snooze, there is a 0.70 probability that he makes it to his first class on time. So there's a 70% chance that he makes it. If he doesn't hit snooze and gets up right away, there's a 90% probability that he makes it to class on time. All right. So it says we want to be able to represent this with a tree diagram. So notice that we have a couple of things happening. We have the chance that he hits the snooze button or does not hit the snooze button, and then we have another sequence of events after that. So if he hits the snooze button, then there's a chance that he makes it to class on time, and there's a chance that he's late. So we can represent this with what we call a tree diagram. So if you look at this, the tree diagram is supposed to represent the cascade of events here. So the first event is hitting or not hitting the snooze button. So there's a 60% chance that he hits it and a 40% chance that he does not. And that's what those probabilities represent. Now, if he hits the snooze button, or should we say, given that he hits the snooze button, well, the probability that he's on time to class is 70%. So notice that this is a conditional probability. The probability that he's on time given that he hits snooze. So these ones here, these guys are conditional probabilities. All right, so basically, this is the multiplication rule in action in a diagram format. So we're going to ask ourselves the following question but before we do that, we're going to define the tree diagram. So a tree diagram basically shows the sample space of a chance process that involves multiple stages. In this case, we had the 2 stages. Now, the probability of each outcome is shown on the corresponding branch of the tree, and all probabilities after the first stage are conditional probabilities, which is what I was saying earlier in the diagram. So now we're going to actually ask the question, and we're going to repost the tree diagram from earlier. What is the probability that in this case it's Steve, hits the snooze button and is late for class on a randomly selected school day? So we're looking for the probability that we hit the snooze button and we want the probability that he's late. All right, well, according to the multiplication rule, right, this means that we need to do probability that he hits snooze times the probability that he is late given that he hits snooze. All right, and how do we do that using the tree diagram? Well, the tree diagram already gives this to us, right? So we know that this is the probability that he hits snooze, which is 0.60. And then we follow the tree, so we have this, and then we have this, that he is, oh, actually, wrong one. We have this one right here. So he's hit snooze and he's late to class. So we times those probabilities as we travel along the tree diagram. So in this case, we have 0.60 times 0.30, and that will give us our probability. In this case, that would give us 0.18 for our probability. So he has an 18% chance of hitting the snooze button and being late to class. All right, so now what is the probability that Steve is late to class on a randomly selected school day? All right, well, so he is late to class. So if he's late to class, well, that means that we are looking for the probability that he's late and he hits snooze. So we'll say that he hits snooze and is late. So we'll say hits snooze and is late, or we want the probability that he does not hit snooze and is late. So either one of those probabilities satisfies this, which means that if we're doing or, we're going to add those probabilities. So this means we're adding those probabilities. So basically, we have 2 multiplication rules, right? We have 2 multiplication rules joined by the plus sign in between. So this is going to be the probability that he hits snooze times the probability that he is late, rather, given that he hits snooze. I'm just going to say HS for that. Plus the probability that he does not hit snooze times the probability that he is late, given that he does not hit snooze. And we'll shorten that as NHS. So basically we have 2 tree diagram problems here, right? We have 2 trees here, one here, one there. So, and we already did the first one earlier, so we don't have to repeat that, but just to show you, we're going to use those numbers again. So 0.60 and 0.30, that one we did earlier. But what about the other one? So plus. So he does not hit snooze, which means going back to the diagram, we're interested in this, so he does not hit it. and he is late. So we're going to be using those two probabilities, and we will times those together. So we got 0.40 times 0.10. And then we get our answer. So we get 0.18 plus 0.04, which is 0.22. So he has roughly a 22% chance that he's late to class on a randomly selected school day. All right, so let's look at another problem. So that one was just sort of like a demonstration problem, if you will. But let's look at an actual problem. So we got the Kaiser Family Foundation recently released a study about the influence of media in the lives of young people aged 8 to 18. In the study, 17% of the youth were classified as light media users, 62% were classified as moderate media users, and 21% were classified as heavy media users. Of the light users who responded, 74% described their grades as good, while only 68% of the moderate users and 52% of the heavy users described their grades as good. Suppose that we select one young person at random. Draw a tree diagram to model this chance process. So if you look at here, this last sentence, of the light users who responded, 74% described their grades as good. That's telling me that that is a conditional probability, right? So keep in mind that the 74% is a conditional probability, and so is the 68 and 52%. So we can demonstrate this with a tree diagram. So we're going to say, let's say we're looking at some students, right? The students in the study. All right, so of the students in the study, well, we know that 17% are described as heavy or as light users, right? So this is a light user. We know that 62% are classified as moderate users. And it says here that 21%, so there's a 0.21 chance, is described as heavy users. All right, now it says of the light users who responded, 74% described their grades as good. So of the light users, 74%, which is 0.74 here, had good grades, which means that of those guys, 26%. Remember, it has to add up to 100% here, right? So 26% of the light users recorded their grades as bad. Now for the moderate users, of the moderate users, 68% described their grades as good, which means that 32% was bad. And we can continue this with heavy. We got 52% described their grades as good, which means 48% were not so good. All right, so that's our tree diagram. Now we're going to answer the next question, part B. Find the probability that this person describes his or her grades as good. So this means we want the probability of good, right? Now the probability of good, well, there's a few ways that you can get to good, right? So you can get to the probability. So the way we can describe this is, well, we can have the probability of light and good, or, which means we add, the probability that you're a moderate user and good, or the probability that you are a heavy user and good. In that case, we have three different multiplication rules that we got to use here, right? So in here we have, well, we got to do the probability that he's a light user times the probability that he's good given light user, plus the probability that he's a medium user times the probability that he's a good user given medium, good grades, sorry, plus the probability that he's a heavy user times the probability that he has good grades, that he reports good grades given that he's a heavy user. So then in that case we have 0.17 for being a light user times 0.74 for being, having reported as good grades, plus 0.62 for the moderate times 0.68 for the good of the moderate, plus 0.21 for the heavy user, and then 0.52 for the 52% of the heavy users. In this case, we get a probability of 0.6566. So the probability that a randomly selected student reports good grades is 65.66%. All right, so let's look at the next problem, example 3. So many women choose to have annual mammograms to screen for breast cancer after age 40. A mammogram isn't foolproof, however. Sometimes the test suggests that a woman has breast cancer when she really doesn't, which is called a false positive. Other times, the test says that a woman doesn't have breast cancer when she actually does, which is a false negative. Suppose that we know the following information about breast cancer and mammograms in a particular population. So 1% of the women aged 40 or over have breast cancer. For women who have breast cancer, the probability of a negative mammogram is 0.03. For women who don't have breast cancer, the probability of a positive mammogram is 0.06, so 6%. A randomly selected woman aged 40 or over from the population tests positive for breast cancer in a mammogram. Find the probability that she has breast cancer. So in this case, we're going to do a tree diagram of this situation first. So we're going to be looking at the women in the study. So of the women in the study, we have a 1% chance that a given woman aged 40 or over has breast cancer. Which means that there's a 99% chance that, a given woman that is selected randomly over the age of 40 does not have. Okay, so of the 1% of women that have breast cancer, we're going to be looking at the whether they test positive or negative, right? So for women that have breast cancer, it says that the probability of a negative mammogram is 0.03. So in this case, for a negative mammogram is 0.03. For a positive mammogram, has to be 97% chance, right, to add it to 100%. And then for the women that don't have breast cancer, well, they have a 6% chance that it says that the mammogram says that they're positive for cancer. So that's a false positive. And then there's a 94% chance that it correctly says that they don't have cancer. All right, so that's our tree diagram for the scenario. So now we want to determine what is the probability that she has breast cancer. And it says that they test positive for breast cancer in a mammogram. So given that she tests positive for cancer, find the probability that she has breast cancer, right? So we're looking for a conditional probability here. Okay, so we're looking for the probability that she has breast cancer so has breast cancer given that they have a positive test. So given that they have a positive mammogram. So what is that conditional probability? Well, we can calculate this conditional probability using the formula for conditional probability. If you recall, the probability of B given A is probability of A and B divided by the probability of A. So in this case, if we use that formula, well, this is the probability of has breast cancer, I'll just say has BC, just to shorten that, and a positive mammogram, so plus sign and M for mammogram, over the probability of a positive mammogram. So that's our formula. So what's the probability of getting breast cancer and having a positive mammogram? Well, in order to do that, we can use a tree diagram for that. Okay, so having the positive, having breast cancer, the chance of that is 0.01, right, for having breast cancer. So we're going to be multiplying these together. So we have the probability that she has breast cancer times the probability that she has a positive reading, positive mammogram, given that she has breast cancer. So in that case, that's looking at these two numbers right here on the tree diagram. So we're going to be multiplying those two together. All right, so let me make some room here because I need some room for this. So let me bring this down real quick because we're going to need to do the denominator for this. So we said we got 0.01 and then that's 0.97. All right, so we're going to need room for the denominator. So how do we find the the probability of a positive mammogram? Well, the only way to do the probability of a positive mammogram is to be able to do both of these scenarios, here and here, right? So we'll have to do the probability that the person has breast cancer and tests positive, or doesn't have cancer and tests positive. Okay, that's the only way of getting this probability right here on the bottom. Okay, so this is the same thing as doing the probability has cancer or has breast cancer. We'll just say BC for has breast cancer times test positive given breast cancer, or does not have breast cancer and the person is test positive given that she does not have breast cancer. So that's the way that you could say positive for that. So now we can do the calculations now. Notice that this is the same thing as the numerator, so we're going to repeat that. So we have 0.01 times 0.97 plus now the probability that she does not have breast cancer according to the tree diagram is 0.99, and then positive is 0.06. So we're going to be using those two numbers. In that case, the probability is 0.14. So you got a 14% chance. So basically, if we swap breast cancer with positive mammogram, right? If you put it in that order, then we got a bunch of calculations to do. Notice that we know what the positive mammogram is given breast cancer straight from the diagram. But if we want to switch that to breast cancer given positive mammogram, we got to do all this work, right, in order to calculate this. So just switching those two events around the conditional probability changes things immensely. All right, go ahead and pause the video, give this problem a try, and then we'll discuss it. All right, so let's discuss the following problem. So we got lactose intolerance causes difficulty in digesting dairy products that contain lactose or milk sugar. It is particularly common among people of African and Asian ancestry. In the United States, 82% of the population is white, 14% is black, and 4% is Asian. Moreover, 15% of whites, 70% of blacks, and 90% of Asians are lactose intolerant. Suppose we select a US person at random. So it seems like the minority seems to be very high on the lactose intolerant spectrum here. So, so that's an observation. So let's construct a tree diagram to represent this situation. All right, so we're looking at the United States, right, only. So we're looking at, U.S., we'll just say U.S. citizens. They don't have, So in that first here, it says 82% is white, so we'll say W. We'll say 14% is black, so B. And then 4%, 0.04 is Asian. All right, so then, so it says of the 82%, it says 15% are lactose intolerant. So lactose intolerant, and which means that 85% are lactose tolerant. For B, 14% of, let's see here, yeah, so of the 14% of the population that's black, it says here 70% is lactose intolerant, which means that only 30% is lactose tolerant. And then finally, for the Asians, of the 4%, 90% are lactose intolerant. And only 10% are lactose tolerant. All right, so we got our tree diagram for the scenario. So now they want us to, this is number one. So now let's do number two. Find the probability that the person is lactose intolerant. So the probability that the person is lactose intolerant means that they could be white or black or African or Asian, sorry. So they could be white or black or Asian and be lactose intolerant. So it could be white, lactose intolerant, or black, lactose intolerant, or Asian, lactose intolerant. And either of those would count as the probability. So we can rewrite this as the probability of W and Li, or, which means or means you add, right? Probability of B and lactose intolerant, or probability of A and lactose intolerant. Which means that we have three multiplication rules. We got to do the probability of W times the probability of lactose intolerant given W, plus the probability of B times the probability of Li given B, plus the probability of A times the probability of Li given A. So we got a bunch of probabilities to multiply. So we're going to use a tree diagram for this. So the probability of W is 82%, so 0.82. The probability of Li given W is 0.15 right there. We're just traveling along the tree diagram. And then the next one's going to be 0.14, 0.70, and then 0.04, 0.90. All right, and then we calculate those probabilities. And we'll see what we get on the calculator. Looks like the probability here is 0.257. So you got a roughly 25% chance of finding someone that's lactose intolerant. That's 1 in 4 people. So on average, if you keep drawing samples of 4 people, that probability in the long run will approximate 1 in 4 people. So that's quite a bit of people that are actually lactose intolerant, finding someone there. All right, so let's see, number 3. So it says, given that the chosen person is lactose intolerant, what is the probability that he or she is Asian? So given that the person is lactose intolerant, so that's a given. So that means that should be given lactose intolerant, the probability of Asian. So that's what we're looking for. So notice that we know, let's see here, given lactose intolerant, probability that he or she is Asian. Okay. So we can actually, yeah. So if we look at the diagram, we can actually rewrite this. So we're going to be using the diagram for this, but before we do that, let's use the formula. So the formula for this conditional probability is the probability of Asian and lactose intolerant divided by the probability of lactose intolerant. So we're going to have to calculate those probabilities. So let's first describe what that means. So the probability that they're Asian and lactose intolerant, well, that's just a multiplication rule. So the probability that they're Asian times the probability that they're lactose intolerant, given that they're Asian, and that we can find from the tree diagram, over the probability that they're lactose intolerant. Well, what's the probability that they're lactose intolerant? Well, we just did that in number 2, right? So we don't have to do all that work again. So because we already know what that is. So this is going to be from number 2. So this is going to be the number from part 2. Thankfully, we did that, so we don't have to do this anymore. So what's the probability of Asian? Well, that's going to be 4% chance of finding someone who's Asian, so 0.04, times the probability of, so we have 90% chance that they're lactose intolerant given that they're Asian. So that's 90% chance, so that's 0.90 over, and then the number that we got from number 2, 0.257. And we can calculate the probability. And so that should be about 0.14. So we got about 14% chance of that happening. And I'm going to double check that answer. So about 14% chance that you find someone that is Asian given that they're lactose intolerant. All right, guys, that'll do it for the video. So I hope that you found this useful, and I'll see you in the next one.